All right, hello again. This is Jeff Scott. I've been going over the Microsoft Security Development Lifecycle, or SDL, field content PowerPoint presentations. We're on number 13 of 14. Now we're going to be talking about buffer overflows. This is our first 300 level or advanced level presentation. We'll get an overview of buffer overflows, and in particular talk about stack-based versus heap-based buffer overflows, discuss some buffer overflow myths, and talk about how to reduce the risk of buffer overflow attacks in code using the Microsoft Security Development Lifecycle. So as we start up, as far as a little bit of an overview, and you've heard this before, and I guess I jumped ahead. I'm just going to read it directly from the slide here. A buffer overflow occurs when data is written into a fixed length buffer and the size of that buffer exceeds the capacity of the receiving buffer. So in other words, you're trying to copy A into B, and A is bigger than the area that you have to hold B. So the excess data often overwrites and corrupts, whatever is in those locations. This can allow a malicious user to corrupt other data, crash programs, take control of programs, etc. Therefore, buffer overflows are among the most serious and dangerous vulnerabilities there are. Buffer overflows are common in apps that are developed in native programming languages like C and C++, not as common in managed languages like .NET and Java. The problem is you can't assume that your app is immune to buffer overflow attacks just because you're using a managed language. It's still a possibility, so developers have to be cognizant of the threat. Plus, it's possible that in your managed .NET or Java code, you're calling some code that is based on a library that was written in C or C++. So, buffer overflows are created in code whenever the secure application or a secure implementation best practice that talks about validating untrusted input data before writing it into a fixed length buffer is not followed. You can have buffer overflows occur on application stacks and heaps, which we'll discuss in just a minute. So what does one of these look like? And we've talked about it before. Imagine that you've got a cup that you use to drink water. The cup represents a fixed length buffer, and the water is placed in this cup represents the data that will be written into a fixed length buffer. So let's look at different ways that the cup can be filled with water. In the first scenario, it's halfway filled with water. Filling it this way is safe because we're within the bounds of the cup. Now consider the scenario where you fill the cup all the way to the top. This is still safe because you have not exceeded the maximum capacity of the cup. But what about in the final scenario here where you exceed the capacity of the cup and you attempt to pour more water into it? In other words, you're pouring more water into the cup than it can actually hold. All right, this results in water being randomly spilled. Well, in the computer world, this spillover is not so random, and it can be used to overwrite important parts of memory. And then, as mentioned previously, malicious users can take control of the execution flow of a process. Let's talk a little bit about application stack frames. So the first type of buffer overflow is the stack-based buffer overflow. In order to understand the internals of stack-based buffer overflows, you have to understand how an application stack frame functions. Here we've got a sample C program called function 1, and it calls a second function called function 2. So let's see what happens on the application stack when this program executes. The first action is the execution of function 1. When function 1 is called, the computer CPU creates what's called a stack frame for function 1. Then it performs a series of steps on that stack frame in order for function 1 to execute correctly. The first step that it has to do is to store any arguments that are passed to function 1. The second step is it has to establish the return, or the address of the next instruction to execute after function 1 has been completed. This is called the saved return address. In this case, the value is the address of function 2, since that's supposed to be executed immediately after function 1. So when function 1 is completed, this address is loaded into what's called the EIP, or Extended Instruction Pointer Register. The CPU then executes whatever instruction it finds at that address. It should be noted here that the saved address is extremely critical because it controls the execution flow of the program. If a malicious user is able to get in and exploit using a stack-based buffer overflow, they'll often try to target this part of memory. Next, the CPU saves what's called a fixed frame pointer that it uses to reference local variables and parameters. All right. On Intel machines, this is known as an EBP, or an extended based pointer. Finally, the CPU reserves space for any local function variables, buffers, whatever it happens to be. In this example, space is allocated for the integer variable called local int, and a 32-byte buffer that's called local buffer, as you see in yellow. The function 1 function then executes, and the CPU loads the saved address, return address, which points to function 2, and it executes the next instruction. The stack frame setup and teardown process is repeated then for the function 2 function. So the same thing goes on. So now let's discuss the internals of stack-based buffer overflows. The primary risk from these kind of overflows, the primary vulnerability is that malicious users may be able to overwrite key memory control structures. If they're able to do that, they can take control of the execution flow of the process. This would allow them to control the instructions and commands that the CPU executes. Here's an example of a function that's called unsafe function. It has a classic stack-based buffer overflow vulnerability using the string copy, strcpy function. If you inspect the implementation of unsafe function here, you'll see that it allocates a fixed length buffer of 32 bytes on the stack called buffer. Then it copies the input parameter, str, which is a character pointer, into buffer using a call to string copy. The assumption is that this code will never exceed, or str parameter will never exceed 32 bytes. And that's an incorrect assumption. Whenever assumptions like these are made, they typically result in the presence of, or at least possibility of, buffer overflow conditions in code. So recall from the previous slide that before the unsafe function actually executes, the CPU creates a stack frame for the unsafe function. Recall also that the return address in the stack frame specifies the next instruction to execute after the unsafe function is completed. This saved address is frequently the target of buffer overflow attacks. Here's some more sample inputs that you could input into the save function. The first is the string Kevin. The second is the letter A that's repeated 40 times. Well, let's start with Kevin. It's only 6 bytes long, 5 bytes for the KEVIN, and the trailing null terminator byte. That fits within the bounds of the buffer. So the function completes, the CPU restores the return address back to the EIP register, and you have normal execution. There's no buffer overflow condition here. But let's check the second one, which has, again, 40 character A's. So the function will copy the first 32 A's into the space allocated for the buffer, but what about the last 8? What happens to these? Well, string copy continues copying the remaining 8 over the saved frame pointer, as well as over the saved return address. So the saved frame pointer and the saved return address have now been overwritten with byte values for the letter A, or hex 0x41. So when the unsafe function completes its execution, the CPU will read the value currently in the saved return address, which is now 0x41414141, into the EIP register and try to execute that instruction. It'll probably cause the process to crash. But a malicious user could have specified their own address there to continue execution. So what would happen if the data stored in the buffer contained malicious code or payload, and the address stored in the saved return buffer pointed to the address of buffer? The CPU would now blindly execute whatever instructions were stored in buffer. That's exactly what the malicious user would want. So let's contrast that with a heap-based overflow. Heap-based buffer overflow attacks exploit buffers that have been allocated on the application's heap rather than the stack. These overflows are a little bit more complex or complicated to understand, and they exploit than the stack-based ones. So let's take some time to look at how heaps actually work. An application heap is a dynamic section of memory. Both heaps and stacks can be used to store data, but they differ in that heaps are allocated at runtime, whereas stacks are allocated at compile time. So heaps are known as being late binded, whereas stacks are known as being early binded. Heaps are useful in scenarios where the size of the upcoming data is not known at compile time, but is known at runtime. So imagine that you were going to create an array, but you couldn't do it. So I was doing a program to figure out grades for my students. So maybe the first thing I ask is how many students are in the class. Then I create an array of that size. And if I run the program again and I give it another class, I could have a different number of students in there. Heaps are basically broken into chunks. Within each of these chunks is a section that stores information about each chunk, such as the chunk size and pointers to neighboring heap chunks in memory, if there are any. Here we're only going to be looking at heap chunk back pointers, BPs, and forward pointers, FPs. The BP is used to point to the previous heap chunk, and the FP is used to point to the next one. This is basically a doubly linked list. So now let's see what happens to the heap when memory is dynamically allocated during normal application execution. Here we've got a C function that's called sample function that simply allocates space on the heap via a call to the cmalloc or memory allocate function. It then performs some operations and then deallocates the allocated heap space with a call to free. So let's see what happens to the heap when this goes on. Chunk 2 is the newly created heap chunk. Chunk 3's back pointer is changed to point to chunk 2, and chunk 1's forward pointer is changed to point to chunk 2. Chunk 2's forward pointer and back pointer are changed to point to chunk 3 and chunk 1. This is handled automatically in the background by the operating system's heap manager. The location of these allocated heap chunks will differ depending on the platform and how the heap manager has been implemented. Chunk 2 is not necessarily going to be placed between 1 and 2, but the pointers will be set up correctly. It's shown like this because it's the easiest way to realize what's going on. After the heap allocation, some operations are performed on the chunk, and the chunk is deallocated via the free function. When a heap chunk is freed, the forward pointer and back pointer of the adjacent heap chunks need to be updated. Finally, chunk 2, after the pointers have been reset, is removed, and the forward pointer and back pointer of adjacent heaps are updated accordingly. So let's examine how a malicious user could exploit a heap-based buffer overflow vulnerability. The primary risk here is when a corrupted heap chunk is deallocated. When this occurs, a malicious user can gain the ability to write arbitrary 4-byte words, basically any place, D words as they're called, anywhere in the application's memory space. And with this ability, they can modify saved return addresses and pointers elsewhere in memory and take control of executing processes. Due to the dynamic nature of heaps, heap-based buffer overflow exploitation is not as straightforward or as reliable as stack-based counterparts. It's harder to do, but it can reap as big, if not a bigger, reward. So here we've got a vulnerable function called unsafe function. the same one that was used earlier when we demonstrated the stack-based buffer overflow. In this version, the allocated buffer is going to be created on the heap rather than the stack. Here's the current heap layout. There's already two heap chunks, chunk 1 and chunk 2 present. So let's see what happens when the unsafe function is executed. Let's also assume that the parameter passed here, there are, again, several cases of the letter A where we've got more than 32, 200 or 300, let's say. The first instruction that gets executed is the call to malloc. This will create or allocate a heap chunk onto the heap with 32 bytes of usable data space. This corresponds to chunk 3. Now let's see what happens when the string copy is executed. So the first 32 A's are written to the data section in chunk 3 as we'd expect. The rest of the A's spill over into the adjacent heap chunk and overwrite the forward pointer and back pointer fields. Now chunk 2 is deallocated or freed, so the malicious user will be able to write the 4-byte D words elsewhere in memory. All right, as you can see in the picture right here. Here on the right side is kind of pseudocode that shows what's going on here. So notice now that where we had valid addresses before, they're replaced with A's, and these A's are placeholders. That could be anything that the malicious user wanted to add. So as we kind of shown here, exploitation of heap-based buffer overflows can be difficult, but it's not impossible. As far as some buffer overflow myths, myth number 1, buffer overflows affect only Microsoft platforms. It's not true. They may be more prevalent or as prevalent on Microsoft platforms, but they can occur any place. Myth 2, buffer overflows cannot exist in applications developed in managed languages, such as the .NET framework and Java. All right, you can't assume that a managed language provides total immunity from buffer overflow attacks. It doesn't happen often, but it can still happen. Myth number 3, buffer overflows cannot be exploited on application heaps. Well, we just saw in an earlier presentation or earlier demo here, this is not true. All right, various operating systems such as Windows, Linux, and others have built-in mechanisms to make exploiting heap-based overflows difficult, but none can guarantee that it will not happen. So how do you reduce your exposure to buffer overflows within the Microsoft security development lifecycle? Well, here's some guidance, so to speak. All right. Reduce your attack surface and implement least privilege. Search for risky functions. Use safer libraries. Use compiler protection. Use code analysis tools, and use fuzz testing. All things we've talked about previously. 2 key design principles here can be used to help reduce the risk from buffer overflow attacks. They are reducing the attack surface, which helps prevent buffer overflow attacks by reducing the possible application vectors that the malicious user can exploit, and the theory of least privilege, which takes the approach of conceding that buffer overflow attacks will happen, but isolates the potential damage caused by these attacks by limiting the privilege level. Reviewing application code for weaknesses that could facilitate buffer attacks before releasing it requires a lot of time, a lot of effort, and possibly a lot of money. The code review process, if done, should not focus solely on preventing buffer overflows, but be employed basically holistically throughout the code to come up with any kind of potential vulnerability. Using safer libraries helps reduce the likelihood of developers performing coding mistakes that could result in the presence of buffer overflow capabilities. Current Microsoft compilers provide protection and features, things like limited stack protection and heap checking, that can be used to help detect certain buffer overruns during runtime. We've talked about the code analysis tools, such things as Microsoft Prefast and SAL, or the standard annotation language, which can be used to help detect vulnerabilities through static code analysis. Fuzz testing. Remember, as it says, it's a testing methodology used to identify security issues that can manifest in apps prior or due to improper input validation. So you can run fuzz tests oftentimes using automated mechanisms, all right, that won't take as much time. Finally, platform protection from buffer overflows. Modern day operating systems inherently provide built-in protection against buffer overflows. They help reduce the risk of buffer overflow attacks on applications. So none of these, again, as we've mentioned several times, are silver bullets. All right, they all must be used in conjunction with one another to work effectively. So this concludes number 13 of 14, our discussion on buffer overflows. When you develop applications in native languages such as C and C++, developers must ensure that any untrusted data being written to fixed length buffers is first validated. Specifically, you must ensure that the size of the data being copied does not exceed the maximum capacity of a fixed level or fixed length buffer. If you do not take this step, your app may be susceptible to buffer overflow attacks. All right, and buffer overflows can be exploited in both application stacks and in heaps. Although it's rare to find it done in heaps, it can be done. Although it's rare to find buffer overflows in trusted languages or managed languages such as .NET and Java, it still can be done. So again, we've now gone through 13 out of the 14 lessons. We have one lesson left, which is on compiler defenses.